Okay, let's continue our discussion of Gibbs energy. Here's a question. How would you calculate the delta G for an isothermal expansion or compression of a gas from P1, pressure P1 to pressure P2? So what will we need to do? We start off with our fundamental equation, dG equals minus S dt plus V dP. Since we're doing it isothermally, this term, first term drops off, so we say delta dG is just V dP. So our delta G would just then be equal to the integral of V dP from P1 to P2. Okay, so what would it be for an ideal gas? Let's say if we knew, suppose we knew that the Gibbs energy is G naught at 1 bar, and what would a plot of G versus pressure look like at constant temperature? Then you would say, in the case of an ideal gas, what would this be? So if you're dealing with an ideal gas, remember earlier we said that was just V delta P for a solid or a liquid because you can factor out the V. For an ideal gas, you won't be able to do that. So volume will just be nRT over V, nRT over P, I'm sorry, dP from P1 to P2, right? So that's just going to be equal to nRT ln P2 over P1. All right. Now let's say, like I said, we knew, what if we knew what the Gibbs energy is at 1 bar, what would be the G at some other pressure at the same temperature? Then you're going to say, okay, this delta G right here would be G minus G naught, right? So it's the difference of G at some pressure, P minus G at 1 bar pressure is equal to, for an ideal gas, nRT ln P over P naught, okay? Because this would be like G2 minus G1. G2 is the Gibbs energy at pressure P2, G1, oops, sorry. Let me rewrite this. G2 minus G1, right? So G2 is the Gibbs energy at pressure P2, and G1 is the Gibbs energy at pressure P1. So G is the Gibbs energy at pressure P, and G naught would be the Gibbs energy at pressure P naught, which is 1 bar. So we say then that G at some other pressure would be equal to G naught plus nRT ln P over P naught. That's for an ideal gas. If it's 1 mole, then we put N equals 1 over there if you want to do it on a per mole basis. So what would happen now if we were to try to plot G versus pressure? What would the plot look like? At pressure P naught, let's just say this is P naught. The value is G naught, so whatever that is, that's going to be G naught, right? And what does a plot of natural log look like? Okay, let's see. It's going to look like this. Okay. Think of it this way. When P is less than P naught, okay, then this natural log of a number less than 1 would be negative, so G would be less than G naught. So you see this left side right here. And when P is greater than P naught, this is going to be a positive number, so G naught plus a positive number, so G would be higher than G naught. So that's how it's going to look. Okay? And if you just remember your plots of log of x versus x. If x is 1, log of x is 0. If x is 10, then log of x is 1. If x is 100, so you can see your graph looks like that. Okay. Let's talk about chemical potential now. For pure substance at a given temperature and pressure, okay, it's pure substance. We'll give you a more general definition of chemical potential later. The chemical potential is just the molar Gibbs energy. It's the Gibbs energy divided by the number of moles. So what we call the chemical potential, which we represent by the letter mu, is the molar Gibbs energy at constant temperature and pressure for a pure substance. Now, values of chemical potentials cannot be determined on an absolute basis because Gibbs energy is U minus Ts, and you can't really give absolute value, an absolute scale for U or G for that matter. We can only determine values of chemical potential in comparison to what we would call a standard state. So we define a standard state, and what we're really just interested in is how the chemical potential in a particular case compares to the standard state. Right? So in the case of an ideal gas, okay, our standard state is a gas that, in the case of gases in general actually, we define our standard state as the situation where the gas is at 1 bar pressure and it's behaving ideally. And unless otherwise specified, we're talking about a gas at a temperature of 298.15 Kelvin, 25 degrees Celsius. So what would be the chemical potential of an ideal gas at pressure P if its standard state chemical potential is mu naught? Okay, so that means when P is equal to P naught, which is 1 bar, mu is equal to mu naught. This is our standard state. Okay. Well, we go back to our expression for G. Remember, G is equal to G naught plus nRT ln P over P naught from an earlier slide. I think we have that right here. Okay. This one right here. I can rearrange this to this one right here. Okay. G naught plus nRT ln P over P naught. So chemical potential is just mu. It's just G over N. So that's G naught over N plus R. N disappears, so RT ln P over P naught. And G naught over N is just the chemical potential at the standard state. So that's mu naught plus RT ln P over P naught. So this is how the chemical potential varies with pressure. Okay, so this is mu versus P at constant T. The chemical potential of an ideal gas varies with pressure at constant T. And it's basically the same thing as what we had, as the plot we have earlier for G versus pressure, because it's simply, all really did was it did it on a per mole basis, so the graph's going to look the same. Okay, so this is P naught, and this is mu naught right here. Okay. What if you're dealing with a real gas? Okay. Here's a strategy we're going to use. We're going to say that the chemical potential of a real gas, that's mu, and I'm just putting an R there to indicate that, to emphasize we're dealing with a real gas, is just whatever the chemical potential is of the ideal gas. And then we'll just introduce a correction term. Okay, so here's a plot of mu minus mu naught right here. Look, that at 1 bar pressure right here, 1 bar, mu minus mu naught is equal to 0, right? So mu is equal to mu naught at P equals P naught. All right. So this is the ideal curve right here. Well, let's say that at some pressure, some condition like this condition right here, at this pressure right here, this is the difference between the chemical potential of the real gas and the ideal standard state, the standard state. Okay, and the ideal prediction would be the point on the red curve right here. So this difference right here, that's going to be the correction that we're going to make. Okay. So what we're going to do is we're just going to say the chemical potential at point at pressure P right here for the real gas, this is your mu, right, minus mu naught, is equal to mu naught, okay, plus RT ln P naught. So this is the ideal value, plus this correction term, which is RT ln gamma. So this difference here, okay, is going to be the difference between the ideal and the real. So it's real minus ideal. Okay, so mu r minus mu I is RT ln gamma. Okay, so this is going to be RT ln gamma. Actually, this is ideal minus real, so this absolute value of this is RT ln gamma. Okay, so if you do real minus ideal, that would be a negative number. Okay, so we can simplify this. We can combine the log terms. Okay, remember ln. Okay, I have combine the RT, factor out the RT there, so that gives you RT times ln of P over P naught plus ln of gamma. And if you remember your identity, ln of A plus ln of B is equal to ln of A plus A times B. So you can just multiply P naught gamma and over P naught, and this is our expression for the chemical potential of a real gas. Okay, the question is, why are we putting the correction term in this form, writing it in this form? The reason is so that we can get something simple like this. Now, is this justified though? No, it's just a correction, right? So it has to be able to account for all possibilities where the chemical potential can be lower or higher. What if it's in this particular case, okay? What is our RT ln gamma here? It's going to be a negative number, right? It's mu r minus mu ideal is going to be negative. Your chemical potential of your real gas is less than that of the ideal. So what does ln gamma here? What is ln gamma over here? Okay, so ln gamma must be a negative number since RT is a positive number. So if ln gamma is negative, okay, then gamma must be a number less than 1. Okay? What if your real gas chemical potential is above the ideal value? In this case, let's say our real value is over here. Then this case RT ln gamma, okay, you have mu real minus mu ideal is going to be a positive number. So it's going to be a positive number. Then ln gamma is positive. Then you say gamma is equal to a number greater than 1. Okay? So what if the gas has exactly the same chemical potential as the ideal? Then that means your correction, RT ln gamma, is equal to 0. So this is mu r is equal to mu ideal. Mu real equals mu ideal. Then that means ln gamma is 0, then gamma is equal to 1. So in other words, what we've done here is we've defined something, gamma, this is called the fugacity coefficient, that gives us an indication of how your real gas deviates from ideal behavior. So if gamma is equal to 1, we say it's ideal, behaving ideally. Its chemical potential is that of the ideal gas, corresponding ideal gas. And if gamma is not equal to 1, it can be less than 1 or greater than 1. And that accounts for all possibilities, all possible correction that you can come up with. Okay, so that would give you your, that gives you an indication of how far you are from ideal behavior. Okay, so this term right here, gamma times the pressure, is defined as what we call the fugacity of the gas. Okay, so chemical potential is just of a gas, a real gas, is just the chemical potential of the standard state, which would be an ideal gas, which would be its chemical potential if it were behaving ideally and if it were at 1 atmosphere pressure. But the gas is not behaving ideally. It's not at 1 bar pressure. But the gas is not behaving ideally. It's not at 1 bar pressure. Then the chemical potential would be whatever the ideal value is. You add RT ln gamma P over P naught, or RT ln fugacity over P naught. So this is the expression for chemical potential of a real gas. Okay. Now, how do we determine the chemical potential? Well, remember, chemical potential is just Gibbs energy per mole, right? So let's calculate delta G then for 1 mole of a real gas. Okay. And let's change it to an ideal gas at pressure P. Okay? So we're going to compare ideal minus real. Okay? What did we have before? We said mu real minus mu ideal. Okay? What we're saying is mu real minus mu ideal is equal to RT ln gamma. Or we can say, okay, I think I wrote it differently here. Mu ideal minus mu real is equal to negative RT ln gamma. Okay, so this is our starting point right here. Okay, if we know the difference between the ideal chemical potential and the real chemical potential, that's just going to be negative RT ln gamma, so you can solve for ln gamma. Ln gamma would be e to the negative mu ideal minus mu real over RT. But mu ideal minus mu real is just delta G. Okay? If you're going from a real gas to an ideal gas at the same pressure, then your delta G, if you're dealing with just 1 mole, will just be the change in the chemical potential. So let's calculate delta G for the change that involves the conversion of a real gas at pressure P to an ideal gas at pressure P. And so let's see. Delta G, let's imagine that as a series of steps, 3 steps. First step is we imagine our real gas at pressure P, lower its pressure isothermally. Okay, remember everything is isothermal, all the way down to a very low pressure, so that at that low pressure it's going to behave ideally. So that's going to be close to 0. We need delta G for that step, delta G1. Okay. Once we have our real gas at very low pressure, it's going to behave ideally. So the change from a real gas at low pressure to an ideal gas at low pressure, delta G for that step, delta G2 is going to be equal to 0. Okay. And then finally, now that we've changed our gas into an ideal gas at low pressure, we raise the pressure of that ideal gas back to the pressure that we want. But it's now an ideal gas at that pressure. Delta G for step 3 would just be delta G for that. Well, if you add delta G1 plus delta G2 plus delta G3, the net effect is you've converted your real gas at pressure P to an ideal gas at pressure P. And so delta G for that process would be chemical potential of the ideal gas at pressure P minus the chemical potential of the real gas at pressure P. And that's going to be negative RT times ln of gamma. Okay? So, what are the formulas for this? We've already known how to do this. So we have the second one right here. Delta G1 is just integral of VdP from pressure P to some low pressure. Okay? V is the volume of the real gas. Remember, dG is minus SdT plus VdP, right? So at isothermal, delta G is integral of VdP. So this is integral of VdP from pressure P to our low pressure. That's step 1. Delta G3 for step 2 would be integral from low pressure P, low P to pressure P, VdP. But this time the gas is ideal, so we write V ideal over here. Okay, so that's total delta G. You add this up, you just get integral of, you can combine the two integrals, but to be able to do this conversion, I have to switch the limits for this first one, right? So that they will have the same limits from low P to whatever the pressure we're interested in. So this becomes a negative V. So that V right there, the real volume, will have to have a negative sign in front of it. And so this is going to be V ideal minus V real, dP from some low pressure P to pressure P. Okay? But what's V ideal? V ideal is nRT over P, where N is 1 since we're doing with 1 mole, so it's RT over P. And V real is V ideal And V real, which is what we call V, is just Z times V ideal. If you remember, compression factor Z is just V over V ideal, right? So the real volume is Z, compression factor Z times V ideal, or Z RT over P. So what we have here is RT over P. So this is V ideal minus V real dP. And that, we say, is going to be equal to negative RT ln gamma. Okay? So we now have enough information to solve for ln gamma. Ln gamma equals, what did I do here? Let's simplify this one right here. Right here, I can factor out RT, it's constant, right? And okay, I'm going to remove that negative sign. I'm going to take the negative of that. So that's going to be 1 minus Z, okay, over P dP. Okay. Integral of that is equal to negative RT ln gamma, and I can just get rid of the negative sign here. So what do I have? Divide both sides by negative RT. I can say ln gamma is equal to negative of 1 minus Z is just Z minus 1 over P dP. And what is Z minus 1 over P dP? Well, if you remember from a virial equation, Z equals 1 plus V prime P plus C prime P squared plus and so on and so forth, after a given isotherm. And if we assume that our pressure is low enough so we can ignore these higher order terms, we can say Z is approximately 1 plus V prime P. Then what is Z minus 1? Z minus 1 would be 1 plus B prime P minus 1 minus 1 plus B prime P minus 1. So that cancels out. So you have Z minus 1 over P. If we divide this by P, that's just B prime. Okay, so this is the second virial coefficient per atmosphere. So this is just right here. This is just B prime dP from 0 to P. I'm just going to make my low pressure 0, take the limit of that at low pressure. Okay, and then so that's just going to be equal to B prime P minus low pressure, which is going to be 0. So it's just B prime P. Okay, that's ln gamma. If we know ln gamma, what can we do now? Solve for gamma. Gamma is going to be equal to e to the B prime P, approximately, okay, over several atmospheres. All right. Let's see what that looks like. If we were to graphically determine that. What would the plot of Z versus P look like? You remember? Ideal gas, Z equals 1, but real gases would typically dip below and then go back up, right? So we're assuming here that our gas is in this region right here. The pressure range is in this region where your Z is equal to 1 plus B prime P. Okay, where a region here where it's essentially a straight line right there. Okay, and you know your B prime is your derivative of Z with respect to pressure, the limit of that as pressure approaches 0, right? So that's we're looking at this interval right here. And what's going to happen there? If you were to plot Z minus 1 over P dP, okay, what is Z minus 1 over P? So that's approximately 1 plus B prime P over P minus 1. It's just going to be approximately equal to B prime, right? So Z minus 1 over P versus pressure within that interval, Z minus 1 over P, okay, versus pressure, is going to be, okay, like this. So within that interval, that's Z minus 1 over P, okay? So this is the value of Z minus 1 over P, right there. If B, that's approximately equal to B prime. B prime, why is it negative? Because you have a negative slope right here. B is negative, okay? So that would be the area under that curve, the negative of the area under that curve. Actually, it's the area above the curve. Right? Now, in general, what would a plot of Z minus 1 over P look like? Z minus 1 over P versus P. Eventually, what's actually going to happen is that the curve is going to look like this. Right? So this is really Z minus 1 over P versus P. So the area is going to start, if B prime is negative, if it dips, then the area is going to start out to be negative, and then eventually the area becomes 0, and then at very high pressure, that area becomes positive. Okay, so that integral becomes eventually becomes positive. It starts off negative, and then later it becomes positive. But what if B prime is positive? Then your plot of Z versus P, if Z is 1 right here, right, versus pressure, this is your ideal curve. Z minus Z versus P is going to look like that, right? B prime is positive. That's the slope as Z of Z versus P as pressure approaches 0. Then your Z minus 1 versus P is going to start off the limit as P approaches 0 would be B prime, which is going to be a positive number. And so your area will always be a positive area. Your integral of Z minus 1 over P dP is going to be a positive number. Okay? So let's apply that. Let's estimate the fugacity of nitrogen at 273 Kelvin at 50 atmosphere, given that the second virial coefficient is negative 10.5 mils per mole at 273. You can look that up. So let's compare that with the literature value of which is 0.9912. So what do we need to do? Go back to our formula. What's the formula we got? Gamma is e to the B prime P. We're just going to make that approximation. The B prime P. What is B prime? B prime is, how is B prime related to B? B prime times RT is equal to the second virial coefficient, right? If you need remembering this formula, a good way to remember is keep track of your units. B, the second virial coefficient, is a volume unit, molar volume. So this is going to be like liters per mole. Okay, or in this case, you're given the value in milliliters per mole. And then B prime is per atmosphere. How do you know it's per atmosphere? Because Z is unitless, 1 plus B prime P. So unit of P is atmospheres, then the unit for B prime is reciprocal atmosphere. So that's 1 over atmosphere. So to get the unit of liters per mole, you have to multiply that by RT, and RT is liter atmosphere per mole Kelvin, and then the unit of temperature is Kelvin. Okay, so Kelvin cancels out, atmosphere cancels out. That gives you liters per mole. So B prime times RT is B. So if we want B prime, so this is going to be E to the B prime. So let's solve for B prime. B prime would be B over RT. Let me quickly do that on MathCAD. And what was RB? RB is negative 10.5. So let me say B prime was B over RT. B prime equals B over R times T. Okay, I need to define what B is. B equals negative 10.5 times milliliter per mole. Okay, and R is 0.08206 times liter times atmosphere per Kelvin per mole. Okay, so now my temperature is 273.15 Kelvin. Alright, that's our temperatures, and our pressure is 50 atmospheres. So now we have, B prime equals, okay, that's the unit. Let me put that in per atmosphere. Atmosphere raised to the negative 1. So B prime is negative 4.684 times 10 to the negative 4. Okay. So negative 4.68 times 10 to the negative 4 per atmosphere. So how do I solve for gamma? I multiply B prime times P, so e to the negative 4.68 times 10 to the negative 4 per atmosphere times 50 atmosphere. So what would that be? E raised to the power B prime times 50 atmospheres equals 0.977. Okay, so you can see it's still really close to 1, still close to ideal. 0.977. That's your gamma. That's your fugacity coefficient. Literature value is 0.911. Okay, so we've assumed that it truncates to the first term in your Viral equation. So that suggests you may have to go beyond that. Okay. All right. Let's see if we can get a molecular interpretation of fugacity. When is F less than pressure? The fugacity less than pressure? Remember, fugacity is gamma times pressure. That means when gamma is less than 1, right? And when is gamma less than 1? When this integral right here is negative. So when B prime is negative. Starts off negative. So when B prime is negative, you start off, okay, first of all, down here at very low pressure, your gas and an ideal gas would match, right? So you have ideal behavior over here. If B prime is less than 0, your gamma is going to start off less than 1. So your fugacity and your chemical potential will be less than 1, less than the pressure, and your chemical potential is going to be less than ideal. Eventually, okay, eventually what happens? Gamma eventually becomes greater than 1. It will always end up becoming greater than 1. So eventually gamma is going to get caught up, and your chemical potential would be higher than and your fugacity will be higher than your pressure, and so your chemical potential will be higher than the ideal. Okay, so that's the kind of curve you'd get if B prime is less than 0. So then fugacity, then you can relate that to intermolecular forces. That would mean what? Gamma less than 1 means what? B prime is less than 0. Negative B prime means you get attractive forces, strong attractive forces predominating, right, initially at intermediate pressures. Okay. Now, what if you have B prime greater than 0? Then at all times, sorry, if B prime is greater than 0, then at all times gamma is greater than 1, and your fugacities would be higher than your pressure. Your correction term will always be higher. So in this particular case, you'll have your chemical potential would be higher than your ideal chemical potential. Okay, so the black curve right here is the real one, the red one is the ideal. Your chemical potential for the real gas will always be higher than for the ideal gas if B prime is greater than 0. Okay, so that's what it would look like. This is for B prime greater than 0. Okay. Finally, let's talk about Gibbs energy of reactions. The standard Gibbs energy of a reaction is given by this symbol right here, delta G, with an R, subscript R, to indicate you're dealing with a reaction. The superscript naught here would be to indicate you're dealing with 1 bar pressure, standard pressure. And unless otherwise specified, this temperature is 298 Kelvin. If it's not indicated, you assume it's 298.15 Kelvin. Okay? The standard Gibbs energy of reaction is defined as just the standard Gibbs energy of the products minus the standard Gibbs energy of the reactant. So that means whatever the Gibbs energy is of the products at 1 bar at that temperature minus the Gibbs energy of the reactants at that temperature at 1 bar. Okay? And you can just calculate that from measurements of delta H and delta S. So remember, G is H minus Ts, so at constant temperature, delta G is just delta H minus T delta S. So if you know the standard reaction enthalpy and the standard reaction entropy, then you can calculate the standard reaction Gibbs energy of reaction. Okay? Alternatively, you can look up tables of the Gibbs energy for standard formation reaction. So this is delta G with an F subscript here. The F is for formation. It's just like your delta H formations. So delta G of formations can be looked up. So the delta G of formation would be delta G for a reaction where you have 1 mole of the indicated product from elements in their standard state. And so just like delta H, you can calculate delta G for a standard delta G for a reaction. This delta G formation of the products minus delta G of formation of the reactants. And looking ahead, we'll see that delta G, the standard delta G of a reaction, is very important because it will tell us how far reactions can go. We can relate it to the equilibrium constant. The standard Gibbs energy of a reaction is equal to negative RT times the natural log of the equilibrium constant. Okay? Let's see what a negative delta, the algebraic sign of delta G means. If your delta G for a reaction is negative, the more negative it is, let's solve for KEQ here. KEQ is equal to E to the negative delta G of reaction over RT. The more negative this term is, okay, then there's a negative there. So negative, that's positive. The more positive that power is, the bigger that exponent is, the larger the KEQ. So a more negative, remember we say delta G negative for a spontaneous process. Well, the standard delta G for a reaction gives you an indication of how far a reaction would go forward. So the larger the KEQ, the farther the reaction would go. Now, delta G of reaction is often used to describe what's called reaction spontaneity. And when we say reaction spontaneity, what we generally mean typically is how far the reaction would go before the reaction is reached. So a more negative delta G of reaction is said to be more spontaneous. Okay? How do we predict spontaneity? For a spontaneous process, okay, delta G is delta H minus T delta S at constant temperature and pressure has to be negative, right? So if you have a process where delta H, so you can look at basically two quantities here, delta H and delta S. Remember, a positive delta S is good, and negative delta H is also good because that's how you can make delta G more negative. Delta G is delta H minus T delta S. Okay, so you want a negative. So processes tend to be favored if delta H is negative and delta S is negative. Okay, so it's positive. I'm sorry. So negative minus a positive will always be a negative number. So if you have a process that has a negative delta H and a positive delta S, that process will always be spontaneous. An example would be a combustion of sugar. You might say sugar doesn't just burn by itself. Well, it requires an energy of activation. But once you provide that sufficient energy to get it going, it will keep going. Okay. So how do we explain this? Think of it this way: delta H, a negative delta H simply means that for that process, when that process occurs, it's going to be dumping heat to the surroundings. Remember, delta H negative means heat flow out of your system. So that will cause the entropy of your surroundings to increase. And the increase in the surroundings and the entropy of the system and the surroundings both increasing, you would expect the process to be spontaneous. Okay. What if delta H is negative and delta S is also negative? So delta H is negative, that's good, right? Because that would make the entropy of the surroundings positive, right? Increase. And delta S negative, that's not good, that's bad. So you remember your expression, delta G is delta H minus T delta S. So this is good with a negative, if this is negative as well, then that's bad, okay? You want to de-emphasize the bad. The way you de-emphasize the bad is you lower the T, okay? So these types of processes tend to be favored at low temperatures. So for example, freezing of water. You go from liquid to solid, okay? See, there's more order here. You would expect delta S to be negative. But when water freezes, okay, they have to lose energy. They have to release heat to the surroundings, okay? So delta H is negative. So freezing of water is favored at lower temperature, okay? So if delta S for the process is negative, okay, that's bad. You have to compensate by putting out more heat to the surroundings as compared to the to pay for that entropy debt. Okay, so entropy delta H has to be negative, and like I said, the way you get a negative delta G is if you lower the temperature. That de-emphasizes the effect of delta S. Okay. Now, we're assuming here delta H or delta S are more or less the same, constant with temperature. It's qualitative. What if it's the other way? What if it's the other way around? Delta H is positive. That means it's endothermic. It's drawing heat from the surroundings, so it's not good, right? So that's bad. But delta S happens to be positive, so that's good. You want entropy to increase. So entropy of the system increases, but it dumps heat to it absorbs heat from the surroundings. So this is bad for the surroundings. Well, again, you go delta G is delta H minus T delta S. This is bad, and this is good. And so the good will win out in this competition, you might say, if the temperature is higher. So this type of reaction will be favored at higher temperature because more of this, the more weight you give to the good, the more negative this delta G is going to be. So the example would be the opposite of the freezing of water, melting of ice. If you go from solid ice to liquid water, okay, delta S for that is positive, but that's also endothermic. For ice to melt, it has to absorb heat from the surroundings. Okay, so delta H positive would mean a negative delta S surroundings, so that's what makes it bad. So delta S of the system has to be positive to compensate for that. And to compensate for that compensate for that, you need a higher temperature to go along with it. Alright, finally, what if delta H is positive and delta S is negative? So delta H positive, endothermic heat flows into the system from the surroundings. So that's bad for the surroundings. So this is bad, and this is also bad, right? Decrease in entropy of the system. This will be decrease in entropy of the surroundings. Then delta H minus T delta S. Okay, this is positive. Minus a negative number will always be a positive number. So this process will be always non-spontaneous. Okay? Delta H positive means delta S would be negative for the surroundings. So system is negative delta S, surroundings is a negative delta S, overall delta S for the universe is 0. So this will always be non-spontaneous. I can't give an example why. It's a non-spontaneous process, an impossible process. Okay? All right, so that's the end of that.